If we recall our understanding of kinetic theory and apply it to the gaseous state, remember that your molecules in the gaseous state are constantly going to be in motion, and they're going to be undergoing collisions, both with each other and also the walls of the container that they're in. Now, what's unique about the gaseous state is that there is a tremendous amount of empty space between adjacent molecules. So as the gas molecules are moving in that constant motion, that independent straight line motion, they're going to travel many, many times, often their own size, their own diameter, before they encounter another molecule to collide with or the wall of the container that they're in. And because there's so much empty space in between adjacent molecules, this is what allows gases to be able to be compressed, much like you would squeeze the air out of a Ziploc bag when you're packing up leftovers. You can apply pressure to a volume of gas and cause those molecules to get closer and closer together. Because gases and the molecules in the gas state are so far spread apart, we treat these molecules, we make an assumption and we treat them as if they are what we call point masses. And what we mean by that literally is we treat them as if the particles have all of their mass, but for all intents and purposes they have no volume and no diameter. And really, when you compare the actual volume of the molecules in the gaseous state to the entire volume that they're in, empty space and all, it's very, very negligible. So under normal conditions, this idea of point masses holds up pretty well. Okay. When we treat gases as point masses, this is referred to as an ideal gas. Now, we know intuitively that that's not 100% correct, but under the majority of circumstances that we would be working with gases and dealing with them, this sort of understanding and assumption works. Because, again, the particles under typical temperature and pressure conditions, your gas particles are going to be very, very far spaced out, and thus this idea of point masses will hold up. Variables that we do need to consider when we talk about the amount of a gas, because gases will assume the shape and the volume of the container that they're in, we have to consider what pressure is the gas at, what temperature is it at, and what volume is it occupying. And they're all four dependent on one another. A fourth variable that we also need to consider is physically how much of the gas do you have? How many moles of the gas do you have? And so if we're going to specify a specific amount of a gas, not only do we talk about, say, its mass or its volume, but we also have to specify the conditions that that measurement is made under. What pressure was it made at? What temperature was it made at? And so we have a standard set of values that is commonly accepted, that if we're going to refer to the mass or the number of moles of a gas or the volume of a gas, we understand that we're talking about measured at a specific pressure at a specific temperature. And those specific agreed upon pressures and temperatures are known as standard temperature and pressure, or STP. Standard pressure is measured to be 1 atmosphere, or 101.325 kilopascals, or any of those other equivalents that we previously defined. And standard temperature is taken to be 0 degrees Celsius, or 273 Kelvin.